Good evening, everyone. Welcome to NPTEL tutorial session for the course Essentials of Oxidation, Reduction, and Carbon-Carbon Bond Formation Application in Organic Synthesis, taken by Professor Yashwant D. Vankar, retired from Chemistry Department, IIT Kanpur. And my name is Sri Lakshmi S. I'm a PhD scholar in the Department of Chemistry in IIT Bombay. So this is our fifth tutorial session. So far in the last four tutorial session, we have been discussing different assignment questions. We have discussed week 0, week 1, week 2 and week 3 assignment questions. And we have also discussed the lecture contents up to week 3 and other problems as well. So today in this session, mainly we will be discussing the week 4 lecture contents followed by the discussion on week 4 assignment questions. So the first topic of the week 4 lecture content was Chamao-Fleming oxidation. So first we will see what is this reaction and how it's going on, the mechanism of the reaction and the selectivity. So as we can see here in this reaction, Tamao-Fleming oxidation is basically the conversion of the silyl group into this alcohol by using this potassium fluoride H2O2, so potassium bicarbonate and methanol. So this was done by Tamao. Then this Fleming, what he did was a modification, that is, silyl group is converted into this hydroxyl group, but by using KBr, this this paracetic acid, and in MCPBA, maybe we can say, not MCPBA, other parasitic acids. So, what is happening actually in the reaction? Silyl groups as a masked hydroxyl group. So, silyl groups are basically converted into hydroxyl group, which was done by both Tamao and Fleming under different condition. So, enantioselective hydrosilylation of alkenes followed by Fleming Tamao Kumada oxidation leads to chiral alcohol. So, if we are starting with, if we are starting with alkene, we can firstly do enantioselective conversion of that alkene into a silyl group, and then we can convert that silyl group into hydroxyl group. So that is the one application of this Fleming Tamao Fleming Kumada oxidation. So in as we can see here, in Tamao oxidation, one ligand of the silicon must be hydrogen or a heteroatom. So here this X either should be hydrogen or a heteroatom. But in Fleming oxidation, all the ligands, SiR2PH, that means all the ligands are containing carbons. All the ligands are of carbon ligands. So that is the difference between Tamao and Fleming oxidation. Now we will see firstly the mechanism of Fleming oxidation. Okay, so in Fleming oxidation, what is happening? A regioselective protonation of the phenyl ring favoring beta silicon effect, silicon hyperconjugation. That is, firstly, what is happening? This phenyl ring, like as we said here, in the Fleming oxidation, all the ligands attached to the silicon are carbon. So one phenyl ring is also attached to the carbon. The first step is the protonation of that phenyl ring favoring beta silicon effect. So this is getting protonated, and we will get this intermediate. So this type of an intermediate having a positive charge on a carbon atom, which is one position away from the silicon. That is, if this is silicon, this is its alpha position, this is its beta position. So this positive charge on the beta position of a silicon atom will have a stabilizing effect on this whole compound, on this whole intermediate. So that is the triggering or the driving force for the formation of this intermediate, that is the driving force for this protonation. So that is silicon hyperconjugation, or we can say beta silicon effect, the stabilizing influence of a silicon atom on the development of a positive charge at a carbon one position away, that is beta position from the silicon atom. So it eventually leads to a reactive silicon intermediate, that is this one, for the further oxidation. Then what is happening in the next step? An X minus will attack over the silicon and this bond is breaking, and this benzene will eliminate and we will get this reactive silicon intermediate. So this will be the reactive silicon intermediate. So what is happening? um, yeah, this phenyl group will be again activated by using bromination, or bromide, or any like anionic species can attack the silicon, and this will lead to the elimination of this whole group, and um, this will be the reactive silicon intermediate. So instead of protonation, what can also happen? A bromination. If you excess bromine, instead of protonation, a bromination can also happen at this position. So in that case, instead of getting this PHH, that is benzene, we will be getting PHBr as the byproduct. So this is the mechanism of Fleming oxidation. So as we can see here, this is Tamawa oxidation. So in Tamawa oxidation, as we said, all the ligands on the silicon are not carbon. One ligand should be at least and one ligand at least should be a proton or a heteroatom. So as we can see here, what is happening here? One ligand is X, which is a heteroatom. So in the presence of this parasitic acid, this HX is eliminating, and this oxygen is attacking over the silicon to form this compound. So this uh, like parasitic acid is attacking over the silicon and this intermediate is forming. Then what is happening is that this bond will migrate over this oxygen and this bond is breaking. So this will eliminate this acetate anion and this whole group will now come to oxygen, and this silicon and this carbon bond is breaking. So that will give this intermediate. So now we can see this R and R1 are attached to oxygen, and there is no bond between this R1 attached carbon and silicon. So this will be the intermediate. Then again, what is happening in the presence of this parasitic acid? Again, this O minus is attacking. mm, no, not O minus. Again, this, yeah, parasitic acid is attacking over the silicon to form this intermediate again. Then what will happen? Again the same thing, this R dash group from this silicon is attacking over this oxygen, this is getting eliminated to form this intermediate. Again what will happen? Same thing will happen in the presence of this parasitic acid. Again it will attack over here, and then again this R dash group will also migrate to that next oxygen to form this intermediate. So as we can see, when we started, all the carbon groups were attached to silicon. Now all the oxygen is attached to the silicon. So that is the difference. Then again what will happen? Again in the reaction medium, this acetic acid or this parasitic acid is there, and this acetate anion is there. So finally this acetate anion will attack over the silicon and it will form this compound. So the positive charge on the silicon will be neutralized. At last, there is no more carbon to be replaced in the silicon. So O minus will attack over the silicon and this intermediate will form. And upon workup, what will happen? This hydrolysis, that is OH minus, will attack over here. This bond will shift over here and this will break, giving this intermediate and our R1OH. So this will be the product. So as we compare the starting material and the product, we can see this whole silicon attached group is replaced with this hydroxyl group. So this is the mechanism for uh, Tamawa oxidation. That is when the ligands attached to the silicon contains at least one heteroatom or one proton. While in the case of Fleming oxidation, we have seen all the ligands attached to that silicon are carbon containing ligands, and the protonation of the phenyl ring takes place, and then attack by a nucleophile will remove the whole group. So that was that mechanism. Now, there are two modifications for this reaction. So, this can either happen in a two port reaction or a one port reaction. So, what is happening in a two port reaction is that firstly, the silyl compound is treated with this any fluoride source, HBF4 or BF3, such a fluoride force, and then that intermediate is treated with MCPBA, like any parasitic acid, to get the product. In one port operation, what is happening directly, the silicon compound is treated with mercuric acetate and this parasitic acid in acetic acid solvent to get this compound, or as we said earlier, bromine in acetic acid, or bromine in parasitic acid, or KBr in parasitic acid can directly give this in one pot. So these are the two different modification, either it can be in two pot or it can be done in one pot as well. So in one pot operation, what is happening, as we said, this protonation, or it will abstract an electrophile to form this intermediate, then X minus will attack over here and this whole group is leaving, that is protodecylylation is happening to form this intermediate. But that is when the reaction is carried out in two ports. But in the case of one port operation, this is not directly formed, we are getting this intermediate directly, that is the parasitic acid is attacking over the silicon and this is forming directly if the reaction is carried out in one port and not this one. Now in this, as we said in the earlier case also, we can see here this, like here this whole group is above and hydroxyl group is also coming above, so this whole operation or this whole reaction take place with retention of stereochemistry. Whichever position the silicon is there, in that position only the hydroxyl group will also be coming. So as we can see here, the silicon is replaced with hydroxyl group and it is coming here, also it is exo and here also it is exo. Here I think this is a mistake, it should be endo, that means or it should be like axial like this silicon. So if starting material, whatever stereochemistry is there, that is completely retained in the product as well. That is one advantage of this Tamao Fleming oxidation. So as we said in Tamawa oxidation, here we saw when it is carried out in two pot, we saw that some fluoride source is used. So in Tamawa oxidation, more reactive fluoro or chlorosilines are used, in which silicon is a stronger Lewis acid and shows more metallic character than the substrates used in the Fleming oxidation. So like what one of the difference between the Tamawa oxidation and Fleming oxidation, we already told, the silicon will be having a heteroatom or proton. So in Tamawa oxidation, fluoro or chlorosilines are mostly used. So in that case, what will happen? Silicon will be stronger Lewis acid and it shows more metallic character as compared to the Fleming oxidation where all the ligands attached are carbon. So here as we can see in the mechanism, firstly when they are treating with this fluoride, it will form this type of a compound, that is a pentavalent intermediate is forming. Then when we are treating with this H2O2, what will happen, this oxygen will attack over the silicon and a hexavalent silicate is forming. Then as we said, this R group will migrate to this oxygen, this will leave to form this intermediate and further it will give the desired alcohol. So here an extra stabilizing factor is there in this hexavalent silicate, that is a hydrogen bonding between this fluoride and this hydrogen. So that is an extra stabilizing factor here. So that is one of the advantages, or one of the more effectiveness of Tamawa oxidation over Fleming oxidation. That is in Tamawa oxidation, uh, since one of the ligands attached to the silicon is a heteroatom, it provides more Lewis acid character to the silicon, and also this hydrogen bonding also stabilizes this intermediate and favors the reaction. Now, these are some of the examples of this Tamawo and Fleming oxidation. So, as we can see here, this SiPHFMe, it is treated with this H2O2, KF, NHCO3 methanol. So, firstly, this fluoride is replaced with this OR, uh, because methanol is used, so this OR will be OMe, or if water is used, it will be OH. Then this whole group is replaced with the hydroxyl group. Then these are Fleming conditions. So, firstly, fluoride will come, and then MCPBA will give this compound. Here also first HBF4 and then MCPBA will be replacing this whole silicon group, and we will be getting this hydroxyl group. Then here is another example. So here what is there, we have this type of alcohol, and this our silicon compound is also there. So this is Tamawa oxidation, because as we can see, one of the atoms attached to the silicon is chlorine. So first step, what is happening when we treat with a base, it will abstract proton of this hydroxyl group. This O minus will form, and O minus will attack over the silicon to form this intermediate. Chloride will leave and it will form this intermediate. Then when we heat under toluene at 190 degrees Celsius, what will happen, this is opening, a heterodyl reaction will happen, and it will form this diene, heterodiene, and this dienophile. So opposite of Diels-Alder reaction is happening. Then again what is happening, so again under this, yeah, so when we are heating, this bond is breaking and this bond is shifting to here, and this is coming over here, so this whole group is leaving. So that is why we are getting this diene and this dienophile. Then this diene and dienophile will react, and another heterodyl reaction is taking place. Heterodyl reaction will take place to give this intermediate. So this is the example for Tamawa oxidation, and which upon treatment with this H2O2, Kf and KHCO3, this Tamawa oxidation take place, and this whole group is converted into hydroxyl group, and here it is already O, so it will be becoming OH. So this is an example for Tamawa oxidation. Now another example is given here. So this alkene is first subjected for enantioselective hydrosilylation. Enantioselective means only one enantiomer is forming. This SiCl3 is coming below, so that we can control by using any chiral ligands or chiral reagents. We can get this one particular enantiomer. Then upon subjecting to the Stamauer Fleming oxidation, this is replaced with this one. So we are starting with an achiral moiety, but we are ending up with a chiral molecule, where this hydroxyl group and the silicon is having the same stereochemistry. Now another example is the reaction of this alkenyl silane. So if alkenyl silane we are treating under any neutral or basic condition, we will be getting this aldehydes, and if we are subjecting it for acidic condition, we will be ending up with carboxylic acid. So in acidic condition means we are using acetic anhydride as an extra acidic source. In basic condition, we are using this methanol THF or this sodium bicarbonate as an extra basic source. So here as we can see what is happening in the presence of an oxidant, that oxidant is attacking over the silicon, that is as we said H2O2 or MCPBA or any acid, paracetic acid can attack, and it will form this compound. Then in the presence of acid, this whole group is leaving, and it will become this aldehyde. Then again if oxidant and acid is there, that will attack over this center and it will form this intermediate. Then it can cleave, like this will take this proton and this bond will shift over here to form this carboxylic acid. So if just two equivalents of oxidants are used under acidic condition, then only this carbon carboxylic acids are observed, indicating that alkenyl carbon silicon bond migrate preferentially to an alkyl carbon silicon bond. So that means um, like this whole group, what to say, yeah, this whole group is migrating to oxygen. If an alkyl group is also attached to silicon and alkenyl group is also attached to silicon, in the mechanism we have seen the migration is happening from the group attached to the silicon, it is migrating to oxygen. So the just preference is given, like alkenyl group will be migrating more faster to oxygen as compared to alkyl group. So that is about Tamao Fleming oxidation. Let me know if you have any doubts regarding the mechanism or the examples which we saw. Okay, now moving on with the oxidations with dimethyl dioxirane, that is DMDO. So this is the compound dimethyl dioxirane, which is a three-membered cyclic peroxides. So this is like MCPBA we will use for converting compounds into epoxides. Like that, this DMDO is also used for the conversion of alkenes into epoxides. So double bond react readily, but electron rich double bonds react more readily with this DMDO. So how it is prepared? This acetone we are treating with oxone. Oxone is the mixture of these three compounds that will give this DMDO. So it is a pale yellow colored liquid with boiling point of minus 20 degrees Celsius. That is, it is very volatile compound. So as we can see here, this alkene, when we are treating with this DMDO, so this DMDO can either be used, we can prepare it and use it in the reaction medium, or in the same pot we can prepare this DMDO. So it will form this um epoxide, that is the product, and this will be the side product. This, so the side product again can be used for the production of this DMDO. So that is one advantage of this reaction. So like this we have seen here, acetone is reacting with this DMDO. Acetone is forming this DMDO. So if we use any other ketone, the corresponding DMDO derivatives we can get. So in situ preparation can be also done, as I said. No need to prepare it earlier and using the reaction medium. Could In situ preparation could be catalytic in ketone, and if ketone is chiral, then enantioselective epoxidation takes place. So whatever ketone we are using here, if that is chiral, our DMDO will also be chiral, and in that case we can control the reactivity, and we can get only one particular enantiomer or one particular diastereomer. So one limitation is that this, if amines and sulfides are present in the reaction medium, that will react very faster than the alkenes. So like N oxides can form, or sulfur oxides can form, that sulfoxides can form. That is one disadvantage of this reaction. But there is no use of any metal or anything. So this is a like more greener protocol, we can say. So these are the two commonly used dioxirane derivative, this DMDO, dimethyl dioxirane, and TFDO, methyl trifluoromethyl dioxirane. So this is one mechanism which happens through the spiro transition state. So this is the DMDO part. So this oxygen will attack over, alkene will attack over this oxygen, then lone pairs will attack over the other carbon and form this intermediate. So stereo selectivity aspects means um, almost in all the cases major product will be formed from the less hindered side. So as we can see here, this will be more where this already presenting group and this epoxide is in the opposite side. That will be the major one as compared to both in the same phase. Then as we can see here, as I said earlier, if we are using any chiral catalyst, like here manganese allen complex is used, which is a chiral catalyst. So that will react with this DMDU and it will form this kind of an intermediate. So it can control the selectivity of the epoxidation. It will block one side and only epoxidation can take place from the other side. So in this case it is happening from the above phase, no, below phase. So two methods are there for inducing chirality on the product. One is that we can use any chiral ligands or chiral metal catalyst can be used. Another is that what we said earlier, we can use chiral ketone. So DMDO, for the dioxirane preparation, instead of acetone or any achiral ketone, we can use a chiral ketone. So that will be helping in installing this epoxide ring selectively. So one such ketone is this one. So this is a chiral compound. So that will help in installing this epoxide only from the one phase. Another example for this is Shy's catalyst. So that is isolated from this D fructose. So from the D fructose we can make this catalyst, and this is also used for doing this kind of reaction in selectively, which will also control the epoxidation selectivity. So these are the different methods by which we can induce epoxidation, or we can carry out epoxidation reaction using dioxiranes, either using chiral metal catalyst or by using starting material chiral ketones, or this Shy's catalyst, manganese allen catalyst. These are some examples for doing epoxidation using dioxiranes and selectively. So we told that either we can prepare this dioxirane and use it in the reaction medium, or we can in situ prepare the reaction medium in the same pot. But in that case, if we are making the dioxirane in the same pot, the problem is that we have to use a two phase system, because this KHSO5, that is not soluble in organic solvent, so we have to use either a phase transfer catalyst or an organic and an inorganic solvent mixture to carry out this reaction if we are generating this dioxirane in the same pot and not using it directly. So that is one disadvantage we can say. So then we also saw that both electron rich and electron deficient alkenes can undergo epoxidation using dioxirane, but electron rich alkenes will be reacting more fastly than electron deficient alkenes. Yeah, as I said, the reactivity difference is there. So here it will react, but the time will be more. So this is electron deficient due to the presence of this electron withdrawing group. So epoxidation is happening, 100% conversion is observed only after 57 hours, so that is taking too much time here. Yeah, this is a very sensitive compound because benzyl groups are there that can get deprotected, and this whole ring can also open. So in that case we can use DMDO because it is not that much aggressive reagent. It can be used for mild neutral condition without any nucleophilic content. So here also same thing is happening, epoxidation is happening, and then if we are hydrolyzing, what will happen, this water molecule will attack over the center, this will open, and then this will leave to form this hydroxy ketone, alpha hydroxy ketone. So here also we have seen earlier, like if electron withdrawing group or electron donating group are there, it generally requires longer reaction time, or sometimes heating is also required, but the products will be stable. If we use hydrolysis condition also, these products will be stable. So that is one advantage of this DMDO epoxidation. Then here are some examples. As we can see here, two double bonds are there. So this is electron rich due to the presence of this 2 methyl group. This is electron deficient because of the presence of this ester. So DMDO will be selectively epoxidizing only this double bond. Electron rich olefin can be selectively epoxidized. Here there is no selectivity. Although this is electron withdrawing, this is electron deficient alkene. There is no other double bond, so DMDO will go and attack over here only, and will get this epoxide. And this intermediate is used in the synthesis of this varucosine 2 beta ol, which is a natural product. This is another example. Like if we are doing this reaction, sometimes decomposition, as I said earlier, hydrolysis can happen. So that can even be used to convert the resulting instead of the epoxide, we are getting here this alpha hydroxy ketone, which we saw earlier. So this is also used in the synthesis of natural products. Now this is the mechanism of that reaction. Like, yeah, so here alkene is there, dioxirane is there. So we told this product we are getting, and what will be the byproduct, whatever ketone we are using as the starting material of this dioxirane, that will be the byproduct. Then if we are using this HSO5 minus, which is from this KHSO5, so that will attack over this center, and this oxygen will attack over this center, and it will form this intermediate. Then what is happening, this, yeah, this OH minus will take proton from this OH, and that will become O minus, and other parts are as such. Then that O minus will attack over this oxygen, and this is leaving. So what is eliminating here is, we can see this SO3 2 minus is eliminating, and we will be getting the dioxirane back. So this is the general mechanism of our DMDO mediated or dioxirane mediated epoxidation. and how this dioxirane is regenerated by using this HSO5 minus. So that is given here. Then if in this intermediate a Bayer vinegar oxidation is happening, what will happen? This whole group is leaving, like as we can see here, if in case this intermediate, this whole like this oxygen lone pair is taking this proton and this bond is shifting over here, so we will be getting this product R C double bond or OR2 ester will be formed. So that is another side reaction that can happen in the case of this DMDO mediated oxidation. That's how this can also form. So that is one side reaction we can say. Instead of getting the epoxide, sometimes we can end up with the esters as well if Bayer vinegar oxidation take place. Because for Bayer vinegar oxidation also we are but generally don't use it, because Bayer vinegar oxidation again needs some paracids. Here if this is acting as a paracid, in that case this reaction can take place. So these are some of the basic concepts regarding this dioxirane mediated epoxidation. The reactions are conducted in buffered, often biphasic mixture. As I said, this phase transfer catalyst, that is PTCs, must be used because this KHSO5 is not soluble in organic solvent. So to bring it into the organic reaction medium, we need some phase transfer catalyst. Then addition of K2CO3 can increase the rate of the formation of DMDO, but it lowers the oxone stability, which is the starting material used in preparation of this DMDO. So higher nucleophilicity of oxone under more basic condition, that is the key for increasing the reaction rate. So if we control the pH, as I said, Bayer vinegar oxidation can take place. Higher pH disfavors Bayer vinegar oxidation. So the catalyst ketone always remains active. So that is one thing we can do for controlling the Bayer vinegar oxidation. Maintain the higher pH of the reaction medium. So decomposition of this oxone at high pH can be overridden if the ketone is sufficiently reactive. Then reactivity of the ketones can be increased if this electron withdrawing group like CF3 is present in the alpha position. This also lowers the rate of Bayer vinegar oxidation. So for lowering the side reactions while using dioxirane, either we can increase the pH of the reaction or we can use um, ketone reactivity can be increased. That will not favor the side reaction, and ketone reactivity can be increased by using electron withdrawing group at the alpha position of the ketone. Then this we already saw this shy catalyst, which is made from this D fructose. So this is this shy catalyst. This is fructose. So that can be used for the stereoselective epoxidation to get only one product. So they have given just what is this OY. It can be either this one or this group or this group. And when it is used, this is used in the case of trans olefin, this is used mostly in the case of cis olefins, and this is used in the case of terminal olefins. Then another reagent which we have seen in the lecture is oxaciridins. Oxaciridin means in dioxirines we have seen it is a three-membered ring having two oxaciridin means it's again a three-membered ring having one nitrogen as well as one oxygen. Then what is its application? It is mainly used in the alpha hydroxylation. So here we can see we are starting from a ketone, and in the product, firstly this enolate is forming and this oxygen will act as the electrophile, and we are getting here alpha hydroxy ketone. Then the same reactions as dioxirane, that is alkene, can be converted into epoxide. Then sulfide can be converted into sulfoxide. Then this amination reaction can also, like RNS2 is becoming this hydrazine type of derivative by using this oxaciridine. Then alkene can be converted into this aciridine, so epoxide can also be made. If nitrogen is used as the electrophile, we can make this aziridine as well. So as we said, if we use oxygen as electrophile, alpha hydroxylation can take place. If we use nitrogen as the electrophile, this alpha amination can take place using this oxaciridines. So this is how this oxaciridins is prepared. Either we can prepare it from this imines or from ketone. For imines, we have to use a peracid. It will give this aciridin, um, oxaciridin. And if we use ketone, we need an amine source. And as we saw earlier, that SO3 salt should also be there to form this intermediate, to form this oxaciridin. So here this nitrogen inversion is not possible in the case of oxaciridine. So if electron withdrawing group is there, it decreases the inversion barrier. So normally we know nitrogen is pyramidal with sp3 hybridization. That is, it is pyramidal, but it is having sp3 hybridization, but the bond angle is less than 109 degree because of the lone pair of electrons present in the nitrogen. So this oxygen which is attached to this nitrogen makes it to have more s character, because more electrons will be pulled over the oxygen and nitrogen will be having more s character. So this nitrogen behaves more mostly like sp2 and lesser like sp3, and this is like more pyramidal in nature. uh, yeah, that is what is given here. Inductive effect of oxygen increases the s character of the lone pair of electrons on n and makes it more pyramidal. So if we use this electron withdrawing group, like here this amide is there or this carbonyl group is there, that will pull the electrons over this nitrogen and make the inversion lesser possible. Now oxaciridins, as we said, either it can convert this alkenes into epoxides or alkenes into aciridine. So either oxygen is transferring or nitrogen is transferring from the oxaciridine. Then its advantages are better reactivity, it can be handled very easily. Then this electrophilic oxygen sources can be used, like oxaciridines, oxaciridinium salt, perfluorinated oxaciridines, all this act as electrophilic oxygen source. So what is happening here is this nucleophile file will attack over this oxygen, this bond is breaking to form this intermediate. Then what will happen, this nitrogen, this negative charge on the nitrogen will fall over here and this will leave. So we will get this one and this one, this will be the product. So as I said, it can act as either oxygen transferring agent or nitrogen transferring agent. If the if the oxaciridine with small substituents on nitrogen, then it acts as nitrogen transfer agent, or those with bulky or electron withdrawing group or nitrogen on nitrogen act as oxygen transfer agents. So as we can see here, the order of reactivity. So if smaller substituent is there on the nitrogen, it acts as better nitrogen transfer agents. And if like bulky groups are there, like here fluorine, no, on nitrogen. So here one R group is there, here two R groups are there. This is MCPBA, then here SO2R is there, then here phosphorus group is there. So this is the order of reactivity for transferring oxygen. So just remember that if bulky or electron withdrawing group on nitrogen is there, it acts as better oxygen transfer reagent. And these are some examples for it: n sulfonyl oxaciridine, that is this one; n phosphenoyl oxaciridine, that is this one; then general oxaciridinium salt, that is this one; and perfluorinated oxaciridines. Then these are the examples for some nitrogen transfer agents: n unsubstituted oxaciridine, n alkyl oxaciridine, or n acyl oxaciridines. This can act as nitrogen transfer agents when we are using oxaciridine for nitrogen transfer. Then here is another reagent, which is oxo diperoxy molybdenum pyridine hexamethyl phosphorus triamide. That is mixture of this two, molybdenum complex and this HMPA. So HMPA is hexamethyl phosphorus triamide. That is this one. This is the other one, that is MOOPH. So what is it doing is basically helping in the alpha hydroxylation of enolate. So this reaction we have seen with both oxaciridine as well as dioxirane. It can be used for the conversion of ketones into alpha hydroxy ketone. So here also same thing is happening. Firstly, LDA will coordinate with this, making the enolate, and OLI will form. Then this oxygen, one of the oxygen will attack over this double bond, or it can coordinate with this double bond, and this lithium will coordinate with oxygen. And then this bond is breaking, and we will be getting this alpha hydroxy ketone. So same thing can be done for this uh, alpha hydroxylation of this nitrile containing compounds as well. So here also LDA will first abstract the proton, and that enolate will form. Then it can form this kind of intermediate, and then hydroxylation can happen. Then this also we already saw, that is how chirality can be installed by using chiral enolates or achiral oxaciridines. So here in this case, the starting material is already controlling the selectivity. So even if there is no particular chiral ligands or chiral group in this oxaciridine, still we can achieve the chirality in the product, and we can get the uh, product in ensure selectively or diasteo selectively. This we already saw, so I am not going into the detail. Maybe I think we can directly go to problems. Yeah. So we will start with this week 4 assignment. Then maybe we will discuss while explaining this. So in the first question, the intermediate that will not form in the following reaction. So this reaction we already saw in the starting of today's lecture. So here we have seen the mechanism, detailed mechanism of this reaction as well. This is converted into this hydroxy compound by using KF methanol and THF in first step, and in the second step H2O2 and potassium bicarbonate. So which will not be the intermediate in this reaction? So this is an example for Tamao Fleming oxidation. Can any of you answer? The intermediate that will not form in the following reaction. Okay, so as we saw in the mechanism of this Stammer-Fleming oxidation, it will form this hexavalent silicate intermediate. So firstly, this fluoride will attack over the silicon and it will form this intermediate. Then when this in the second step, H2O2 is attacking over the silicon. This intermediate will be forming, which will be stabilized by this hydrogen bonding as well. Then this R group will migrate from the silicon to this oxygen, and this will leave to form this intermediate. So these are the three possible intermediates involved in this Tamavo oxidation. So other than this, what is given here is this one. So this one is not a possible intermediate in this one. So this we already saw, that is this one. Then this one we saw, that is this one, then this is this one. So this is not a possible intermediate in the case of Tamawa oxidation. Moving to the second question, in the following reaction, the products that form as major product. So this compound upon treatment with this acetone and this perchloroacid in the first step and in the second step with PCC in DCM, which will be the major product here. So what is happening in first step and what is happening in second step? Can any of you answer this? This is very simple question, right? Okay, so here what is happening? Firstly, acetone and this perchloroacid that is used in catalytic amount. So, acetonide protection, that is diol will be protected by this acetone. So here we can see 1, 2, 3, 4, 5 hydroxyl group are there. So which diol will be protected? So that is one thing we have to consider. So as we can see here, this acetonide protection would occur with 1, 2 cis diols or diols in which both oxygens are readily available for acetonide formation. So 1, 2 diol at the anomeric position and 1, 2 diols at the 3 and 4 considering anomeric carbon as 1 would readily undergo acetonide protection. So 1, 2 diol means either this can undergo protection, this can undergo protection, or this can undergo protection. This cannot undergo protection because this is 1, 2, 3, 1, 3 diol. So acetone is generally used for the protection of 1, 2 diols. So here obviously this 2 will undergo protection. This cannot undergo protection. Then what will happen? This also cannot undergo protection because this is above and this is below. So rather than that, this is more favored. Both are below, so this protection will be more favored. So what will happen? This also will undergo protection and this also will undergo protection, and only this hydroxyl group will be free. Only this hydroxyl group will be free. So in the second step with PCC, this hydroxyl group will be oxidized into the corresponding ketone. So the correct answer would be option 3. This is protected with acetone, and this will undergo oxidation to give this ketone. Is it clear? I hope it's clear. Moving on to the next question. In the in situ prepared DMDO from a ketone and oxone mediated epoxidation of an olefin, the intermediate which can give the undesired ester. So we saw that this undesired ester is formed as a result of the side reaction in the case of dioxirane mediated epoxidation. If bare vinegar oxidation is taking place, that can give rise to the ester instead of getting the epoxide, or this can form as a side product. So for that side product formation, which intermediate will give that undesired ester? So here we have already seen the mechanism. This will be the intermediate which will undergo bare vinegar oxidation. So what will happen? This R group will migrate over this oxygen and this is eliminating. HSO4 minus will eliminate and we will get this ester. So this undesired ester will form. And if in the case of normal DMDO mediated oxidation, this oxygen will attack over here and this will eliminate to form the dioxirane and that will convert the alkene into epoxide. If this is happening, ester will be forming. So this is the side reaction for dioxirane mediated epoxidation. Moving on to the next question, the major product in the following reaction. So this reaction mediated by LDA and this molybdenum complex in THF, which will be the major product here. So this also just now we saw. So this, as we said, upon treatment with this LDA, here one proton is there, so that is acidic proton. LDA will abstract this proton and then hydroxylation will happen at this position to give this compound. So hydroxylation of the corresponding anion treatment with LD occurs from less hindered side. So as we can see, either if hydroxylation can happen, this can form or this can form. But OH minus will be attacking from the less hindered phase. Here in the above phase, this whole group is there. It is a camphor derivative. This geminal methyl group are there and this bridgehead methyl group is also there. So that will provide steric hindrance. So OH minus cannot attack from this side. It will be attacking from this side. So one will not be forming, only two will be the major product. Now the next question, the major product that forms in the following reaction. So here this alpha chloroketone is treated with this chiral compound in the first step and NaH, then LiHMDS, then this oxaziridine, then in the last step LiOH followed by neutralization. So what will be happening in each of these steps and what will be the final product? Can you answer this at least? What is happening in any of the steps? Okay, so in the first step, what is happening? This NH uh, will abstract the proton from this one, and then this nitrogen lone pair will attack over this center, and this chloride will be leaving to form this compound. So this is basically a chiral auxiliary. So it will help in installing chirality. So chiral auxiliaries are basically compounds which we install in a compound which is not chiral for a temporary period of time, so that the next reactions will proceed enantioselectively or diastereoselectively. So once the next reactions are proceeding selective stereoselectively, then later we can remove this chiral auxiliary. So that is temporary attachment, like protecting groups we can say. But protecting groups we are using for protecting it, that particular group from other reaction. But chiral auxiliary we are using because our starting material is not chiral, but we need our product to be chiral. So what we will do, we will attach a temporary chiral auxiliary to the substrate. So the next reactions will be proceeding in a stereoselective manner, because this is a chiral compound. Due to the stereochemistry of this methyl and phenyl groups, the next reactions will be proceeding in a chiral way. So after, once our all the chiral centers are installed in the selective manner which we need, we can remove this chiral auxiliary. So in the first step, the attachment of chiral auxiliary will give this product. Then in the second step, we are treating with LiHMDS. So what will happen with LiHMDS? It will abstract proton from this center, that will form this enolate. So here also this can coordinate with lithium from LiHMDS, and this oxygen will also coordinate with the lithium. So it will abstract proton from here forming enolate, which will coordinate with the lithium, and this oxygen will also coordinate with the lithium to form this intermediate. Then in the next step, what we are doing is we are using this oxaceridine. So enolate is there, so epoxidation kind of reaction or alpha hydroxy ketones are forming with this oxaceridine. So as we can see here, since this phenyl ring and this methyl group is below, this hydroxy group is coming from above phase. So if we are not using any chiral auxiliary, there is no selectivity. Hydroxyl group can come either from above or from below. And if we have used the opposite chiral auxiliary, where this methyl and this phenyl group were above, hydroxyl group will be coming from below. So depending on which product we need, we can vary this chiral auxiliary. So that is one advantage of chiral auxiliary. If we need alpha product, we can use the opposite chiral auxiliary, or like this, if we need beta product, this chiral auxiliary can help. So basically it is providing steric hindrance, or it is blocking one phase, so the reaction can happen only from the other phase. So once our chiral, the purpose of chirality is done, we have got the alpha hydroxy ketone selectively from the one phase. Then for removing this chiral auxiliary, we are using this LiOH. So that OH minus is attacking over this center, and this whole group is leaving to form this product with hydroxyl group, but only at one position, that is above. So that will be the answer. The correct answer would be option 2. Is it clear? Any doubt in any of the steps? First step, attaching chiral auxiliary, then enolate formation, then alpha hydroxy ketone, and then removing chiral auxiliary. Okay, now moving on to the next question. The major product in the following reaction. So this compound, upon treatment with this photochemical condition in presence of iodine, and then methyl wittic salt, which will be the major product. So this reaction we didn't discuss, so through this problem we will discuss this reaction. This is a named reaction already taught in the lecture. Might be you might have heard about this reaction, or can you try to see what will be happening here, which is the possible product. So here, this is an example for Barton
Yeah,
reaction.
yeah, yeah.
Hello. Okay. So this is an example for Barton reaction. What is happening here is, um, yeah, I will just quickly show what is happening maybe. Yeah, so this is Barton reaction. So in Barton reaction, what will happen, we are starting from this kind of nitro compound, and this photochemically this bond is cleaved. So here oxygen radical will form and this NO radical will form. Then uh, this will interact with this proton and it will form the six membered cyclic transition state, and that will break this bond homolytically, and this proton will combine with this oxygen radical to form OH here, and one radical will be generated at the center. So as we can see here, for the formation of the six membered cyclic transition state, one, two, three, four, alpha, beta, gamma, delta. Delta proton should be there for this reaction to happen, and for this six membered cyclic transition state to form. So delta hydrogen abstraction will take place to form this intermediate. Then NO radical will attack over this radical will combine with NO radical and it will form this compound. So abstraction of hydrogen from delta carbon, this is the very crucial step for this Barton reaction. So that is the general Barton reaction mechanism. And here we can see this compound. So here if we see delta hydrogens, this is alpha, beta, gamma, delta. So this is one delta carbon and this hydrogens are delta hydrogen, but this is not happening in this way because of the uh, like this six member transition state is not so easily because of the steric hindrance. So the distance between alkoxy oxygen and delta carbon is too large for hydrogen abstraction. In that case, this reaction doesn't take place. So as we can see here, in the transition state, the carbon, hydrogen, and oxygen atoms are approximately linear in nature. Then only the six membered cyclic transition state will be formed. So, if iodine is used in the reaction medium, iodine will help in this reaction. That is, firstly, the six membered cyclic transition state will form. Then, this iodine will form I radical that will combine with this radical to form this intermediate. Then, which upon oxidation can give this oxidation of this alcohol to get this aldehyde, or if directly any base we are using, that base can abstract this proton and that will attack over here and I minus will leave to form this compound. Or in this case, if further this aldehyde we are treating with the base, means that can form this kind of like, it will remove this one and one two, yeah, that will base will abstract this proton which is acidic in nature, and that will attack over this center to form this three membered ring, and this I minus will leave. So these are the different possibilities or modifications of this Barton reaction. So now consider this question. Yeah, so here what is happening, same thing is happening. Firstly, this bond will break forming O radical over here, that is given here. Then delta hydrogen abstraction can take place, but here as we said, in the for delta hydrogen abstraction it should be more free, like six member transition state formation should be easier. So here as we said, six member transition state formation is not easy. So what will happen, this radical, this bond is breaking here, so one radical will form at this center and one radical will form at this center. Then these two radicals will combine to form here C double bond O, and this radical will be free here. Then that will react with this I radical to form here iodine, which will give this compound. This will be the intermediate in the first step. Upon treatment with photochemical condition and I2, we will be getting this iodoaldehyde. Then in the second step, methyl olefинation is happening, which will convert the corresponding aldehyde or ketone into this C double bond O will be converted into C double bond CH2. So it is an example of Barton reaction wherein distance between alkoxy radical that will form upon photolysis and delta carbon is too large for hydrogen abstraction. Therefore, alpha cleavage is happening. Here this alpha bond is cleaving. and then further reaction methyl Wittig olefination is happening to form this compound. So the correct answer is option 3. So Barton reaction, the one thing you have to remember is six membered for transition state should be formed. So if that is not favoring, alpha cleavage will be preferred over delta hydrogen abstraction. Now the seventh question, identify A and B in the following sequence of reactions. So firstly, ONO photochemical condition, so Barton reaction is happening. Then upon heating another product B is forming. Then PCC oxidation is giving this product. So identify A and B. So here what will happen? First step is Barton reaction. So first step, this will cleave, O radical will form, then alpha, beta, gamma, delta. So from here, this delta proton abstraction will take place, forming radical over here. That will combine with this NO to form this compound. So the first step will be Barton reaction, which will give rise to this compound. Then in the second step, we are heating this reaction. So what is happening in that? The oxime upon treatment with H plus or heat leads to CHO, and the entire molecule turns out to be a hydroxyaldehyde. So yeah. So this upon heating, this will be converted into this hydroxyl group. That is H plus we are using, acid we are using. So that water will be there, that will attack over here, and this whole group will be converted into corresponding hydroxyl group. So this first one will be A1 and second one will be B2. Then if we see this, if we are oxidizing with PCC, what will happen? This lactone formation is taking place. So this will attack over this carbon and this will become OH. Then that OH is further oxidized into ketone by using PCC. So the correct answer would be option answer A1 and B2. That is option 2. Now this is the last question. Okay, here answer is already there. The structure A in the following sequence of reaction. So this compound upon treatment with this NIS in photochemical condition is giving a product A. Then upon hydrolysis we are getting this diol. So which will be the A intermediate? So here, as we know this is the benzyl group, that is CH2 phenyl group, which upon this H nu condition. So NIS is a hypohalite based reaction triggered by NIS. So what is happening? This alkoxy radical abstract benzylic hydrogen at the delta carbon, leading to the radical formation, which eventually forms the acetal. So firstly, this is cleaving, and here O radical is forming upon photochemical condition. then that O radical will abstract this proton. So this is alpha, beta, gamma, delta. So delta proton is abstracted. So here radical will be forming. So that will give this intermediate. Then in the next step, what is happening? Or next, what will happen? An acetal is forming. That is again, yeah, here this proton will go and O radical will form, and that O radical will combine with this one, and one, two, three, four, five. A 5 membered ring will be formed. That is this one. Then this hydrolysis will deprotect this whole group and remove this whole group to give this diol. So that is happening here under photochemical condition. Firstly, this compound will be formed, then this bond is breaking, radical is forming, delta proton abstraction is taking place. Here radical will form again, that will cleave, and this radical will combine and give this compound. So with this, then we will conclude today's session. If there is any doubts or questions, please ask. We will solve the next assignment question, and if possible, some more problems in the next session. And we will discuss the next lecture contents, that is week 5 lecture contents, in the next session. Next session will be on next Saturday 5 o'clock. Yeah, so if no more questions, you can leave. Thank you for joining.
Thank you, ma'am.
Yeah.